A video on alkanes and cycloaklanes. Introduction. The simplest organic compounds are hydrocarbons, the compounds containing only carbon and hydrogen. Depending upon the framework of carbon atom in their molecules, the hydrocarbons may have either open chain or ring structure. In addition, they may be saturated or unsaturated in character according to the nature of the carbon-carbon bond in them. Due to these variations, hydrocarbons have been divided into different classes. We shall discuss the various classes of the hydrocarbon one by one, starting with alkanes and cycloalkanes. Structure of alkanes. Alkanes are open chain saturated hydrocarbons having the general formula CnH2n plus 2, where n is the number of the carbon atom. They contain only single covalent bond between carbon and carbon and hydrogen in their molecule, as each carbon atom is bonded to 4 other atoms. It is clear from the formula of methane, ethane and propane, the first three members of alkanes. The bonds in alkanes are formed by the overlapping of sp3 hybridized orbitals of each carbon atom with similar orbitals of the carbon atom or one s orbital of hydrogen atom. As a result, all the four bonds linking the carbon atom with other atoms are sigma bonds. As the bonds are quite strong, then they are easily attached by the reagent. Alkanes do not react with usual laboratory reagent under ordinary conditions. That is why they are formed saturated hydrocarbons or paraffins. That in paraffins little paraffins mean affinity. It may be also be noted that due to the sp3 hybridized of the carbon atom of the alkane, the four bonding orbitals of each carbon are directed towards the four corners of tetrahedron. For instance, let us consider the case of methane, the simplest alkane. In the formation of molecule, the four sp3 hybrid orbitals of only carbon atom overlap one s orbital of the four hydrogen atom with the saturated on the corners of the tetrahedron. In figure from 4.1, A and B represent a molecular model of the methane. 4.1c is the simplest. There three-dimensional representation of the molecule. In this represent the waves represent the bond pointing towards the observer out of the plane. Paper has the represent the bond going away the observer behind the plane of the paper. Normal lines show the bond in the plane of the paper. Each carbon-hydrogen bond has the length of 110 picometer or 1.10 angstrom, and each CH bond is 109 degree 28 minutes. I have to say information and structure of the methane. Similarly, in case of ethane, 4.2 structure have higher alkane with relative arrangement of bonds already tetrahedral. Although the different bonds angles may be slightly different from the regular tetrahedral value of 109 degree 28 minutes, the CH bond length is about 110 picometer 1.10 angstrom, while the carbon-carbon bond length is 154 picometer or 1.454 angstrom or nearly so. Model of ethane. On account of the tetrahedral arrangement of the four bonds are formed by the carbon atom, the molecule of ethane are three-dimensional in nature. Moreover, in case of alkanes containing more than two carbon atoms, the carbon atoms of the chain do not actually along a straight line. This is quite obvious from the model of the propane shown in 4.3. In fact, higher alkanes, the carbon-carbon chain can assume a variety of zigzag shape, but the sake of the convenience, the carbon atom are written in the straight line, so are possible to the planar representation as shown as below. Classification of the carbon atom in alkanes. The carbon atoms represent the alkanes can be divided into four categories as given below. Primary carbon atoms, it is the carbon linked directly to the either or no carbon atoms. Second is secondary carbon atom. It is the carbon atom which is linked directly to the two carbon atoms. Tertiary carbon atom. It is the carbon atom which is linked to the three carbon atom. Fourth is quaternary carbon atom. It is the carbon atom which is linked directly to the four carbon atom. For example, in the formula given below, the five primary, one secondary, one tertiary and one quaternary carbon atoms hydrogen atom are classified as primary, secondary, and tertiary according to they are linked primary, secondary, and tertiary carbon atom respectively. This in the example given above, there are 15 primary hydrogens, they three each on 5 CH3 groups, and 2 secondary hydrogen on the CH2 group, and 1 is a tertiary hydrogen on the CH group. Nomenclature of the alkanes. The common NIPC name of the naming saturated hydrocarbon are discussed below. The common system. According to the system of the first name member of saturated hydrocarbon are special name, while the higher member are named according to the Latin or Greek numericals indicating the number of the carbon atom in the molecule. The name of all the members end in N as thus CS4 is methane, C2H6 is ethane, C3H it is propane, C4H10 is butane, C5H12 is pentane, C6H14 is hexane, C7H16 heptane, C8H18 is octane, C10H12 22 is decane, and C20H42 is isocane. In the case of isomeric alkanes, from C4H to N onwards, the following discussion are made in naming the various isomers. First is the hydrocarbon having all the carbon atom in a straight or continuous chain are termed normally of an hydrocarbon. For example, CH3, CH2, CH2, CH3 is called N-butane, while the CH3, CH2, CH2 is named as the N-pentane. Second is branch changed isomer in tertiary carbon atom are known as the isom, while those containing a quaternary carbon atom on the term, for example, are isobutane, isopentane, and neopentane. Second is alkyl groups. The removal of one hydrogen atom from the molecule of alkane with an monovalent group called alkyl group, as it is the general formula SCN H2N plus 1 and usually represented by the letter. The name of the alkyl group are obtained by the replacing the suffix "an" is the name of corresponding alkane by YL. It may be possible to yet more than one alkyl group form an alkane depending upon the position of the carbon from which hydrogen is removed, as illustrated below. Name and formula of the alkane is methane is CH4, methane is CH3, CH3. Formula name and abbreviation of the alkyl group. CH3 is methyl, and CH3 CH2 is ethyl. Propane, CH3 CH2 CH3 is propane, and the CH3 CH2 CH2 is N-propyl. CH3CH or CH3 is isopropyl. N-butane is divided into N-butyl, sec-butyl, or isobutyl, or isobutane is divided into tetrabutyl. IPS system straight chain alkanes. The alkanes in which all the carbon atom are represented in straight chain are named by the adding the suffix "an" and the associated word root. For example, the methane, ethane, propane, and butane. Branch chain alkanes. In the case of branch chain alkanes, the largest possible continuous chain of the carbon atom is selected. The corresponding word root followed by the suffix "an" is down the chain is numbered from which the lowest number of the carbon atom is substituted alkyl groups. If the number of the substituent group is more than one, numbering is done by the end according to the lowest set of locants for the branching alkyl groups. The name of the branching alkyl groups along with their branchment members and their prefix before the word root is alphabetical order are illustrated below. 2-methyl-propane, 2-methyl-butane, and 2,2-dimethyl-propane. Next example is for ethyl 2,2-dimethylhexane, and next example is for methyl 3,6-dimethyl-octane. Some important points for giving IPSC name. Few important points to be remembered for the IPSC names of the alkanes are given below. If the two different alkyl groups are equidistant from the two ends of the parent chain, the numbering of the chain is done in such a way that the groups that which come first is alphabetical order gets the lowest number. For example, 3-methyl, 6-methyl-octane. Since ethyl comes ahead of methyl is alphabetical order, the parent chain is numbered from the end of the which lowest number of the ethyl group. If the group attached to the parent chain is also branched, sometimes called a complex substituent, it is named as a substituent alkyl group by separately numbering the carbon atoms of this group. For the purpose of the carbon atom of the group which is attached to the parent chains are always numbered as 1. The name of the such group is always written in brackets. For example, 7 methyl, 2 methyl, 5 2 methyl propyl nonane. That is the deciding their alphabetical or the complete name of the complex substrate, including the prefix such as di and tri forming the parts of the name is considered. For example, the 5,1,2 dimethyl butyl 7-methyl 2-methyl decane. The alphabetical order of the name of the complex substrate is decided as the base of the letter D because it is the first letter of the complex name of this group. For the name of the compound, if two equal long chains are possible, but the number of the side chains attached to each possible chain are different, the possible chain having the largest number of the side chain is selected as the parent chain. For example, the 3,5-dimethyl 2,4-dimethyl correct chain is a 4 chain side chains. Structure isomers in alkanes. Each of the first three members of the alkanes, methane, ethane, and propane, has a evenly structured formula, that is methane, ethane, and propane. The higher member of the butane onwards represent more than one structured formula and thus exhibit structural isomers. The various isomers of the same hydrocarbon differs in the framework of the chain of the carbon atoms, and therefore the isomer exhibited by the alkane is termed as a chain isomer. For example, butane C4H10 is exists in the form of two isomers shown in the N-butane and the isobutane. Similarly, pentane C5H12 exists in the form of three isomers N-pentane, isopentane, and neopentane. C6H14 exists in the form of 5 isomers, C7H16 has 9 isomers, and the C8 and H18 has 18 isomers, and so on. Natural sources of the alkanes. Petroleum, which occurs naturally below the surface of the earth, is a mixture of many hydrocarbons, most of which belong to the alkane series. Natural gas, which is from the petroleum feed, and fuel gases obtained from the coal, contains lower alkanes. The waxy constituent of some plants have also the may found in contain alkanes. For example, pine wood and turpentine oil contains N-heptane, while the leaves of the cabbage contain N-nocanes C29H60. General method of preparation. The preparation of the alkane by synthesis method is only rarely carried out. The usual practice is to isolate their hydrocarbons, particularly the lower ones. Stable natural resources. Some of the general methods which can be employed for the preparation of the source. However, some of the general methods are employed for the preparation of the discussed below. First is hyperconjugation. Saturated hydrocarbons, stable and Sandwich reaction. If alkanes and alkanes can react with hydrogen in the presence of catalysts, finally divided nickel, platinum, and palladium to form alkanes. CN to H2N plus H2 in the presence of nickel 525 to 575 Kelvin, then it forms the CnH2n plus 2. We have further examples. Then into CH triple bond CH plus 2 H2 in presence of nickel 525 575 Kelvin temperature, then it forms the CH3 CH2 ethane. The use of nickel as a catalyst for hydrogenation requires a temperature of about 525 to 575 kelvins, but for platinum or palladium is used as catalyst. The reactions can also take place at the room temperature. Methane cannot be prepared by the method as starting alkanes or alkynes must contain at least 2 carbon atoms. Second is reduction of alkyl halides. Alkyl halides can be reduced directly or through the formation of the Grignard reagent to form alkanes. First is direct reduction. Direct reduction of the alkyl halide is generally carried out by the chemical reducing agent such as zinc and hydrochloric acid, or zinc, copper, carbon and alcohols, or with hydrogen in presence of palladium catalyst. Next is alkyl halides, then it form the RH alkanes. Isopropyl chloride, then it forms the N-propane. The reaction may also be carried out by the heating the alkyl halides, particularly iodides, with hydrogen iodide in the presence of red phosphorus in a sealed tube. For example, ethyl iodide in presence of red phosphorus, then it forms the ethane plus I2. Second is reduction through the formation of the Grignard reagent. This is the indirect method of the reducing alkyl halides. A solution of an alkyl halide is dimether is treated with magnesium to form an ethanol solution of the alkyl magnesium halide, commonly known as the Grignard reagent. Alkyl halide in presence of dry ether, then it forms the alkyl magnesium halide or Grignard reagent. The Grignard reagent are easily decomposed by the water producing alkanes. The Grignard reagent, then it forms the alkanes, and the ethyl magnesium iodide, then it forms the methane. It may be pointed out the alkanes or alkyl halides used for preparation of the alkyls by the above-mentioned method are themselves generally obtained from the alcohols, but the alcohols cannot be directly converted into alkanes by the hydroxy group of most alcohols resist reaction to corresponding alkanes. The third is Wurtz reaction. The reaction brings about the union of the two alkyl radicals by the action of the metallic sodium upon alkyl halide in dry ether. The resultant product are alkanes and a carbon selecton having a higher number of carbon atom and the reacting alkyl halides. Alkyl halides in dry ether then form the alkanes, and methyl halide in presence of dry ether then it forms the ethane. Ethyl bromide in presence of dry ether then it forms the butane. It may be noted that when the reaction involves the two show the same alkyl halides, symmetrical alkanes having one number of the carbon atom is formed for preparing enhanced symmetric alkanes containing 3 or more than the 3 carbon atoms. For example, propane, a mixture of different alkyl halides has to be used. Methyl bromide plus ethyl bromide and from the propane plus 2 MBR. But the products obtained by the using different alkyl halides consist a mixture of alkanes which cannot be easily separated. This the two alkyl halides also react separately with the sodium to form two more hydrocarbon is product of the side reaction. This thus is in case of the above reaction, ethane from the CS3Br and butane from the C2H5Na and are also obtained. The main feature of the Wurtz reaction is that it leads to the formation of the carbon-carbon bond, and such a reaction can be employed by the preparing compounds containing higher number of the carbon atoms from the containing lesser number of the carbon atom. For example, ethane may be prepared by the ethane follows. The order of the reactivity of different alkyl halides in the reaction are first is iodide, then is bromide, then is chloride. Limitation of Wurtz reaction: it is stable only for the preparation of the symmetric alkanes. Second, it is cannot be used for the preparation of methane. Third is the tight alkyl halides cannot be used in this reaction. Two mechanisms have been suggested for this reaction. These are intermediate formation of the free radicals. According to this mechanism, it is believed that the alkyl halides first forms alkyl radicals which combine with only one another to furnish by the hydrocarbon. Thus, mechanism operates when the reaction is carried out in the vapor phase. Second is the intermediate formation of an organometallic compounds. Here the reaction is believed to be place through the formation of the organometallic compounds as intermediate. For example, this mechanism operates when the reaction is carried out in the solution. For this Corehouse synthesis, this method was developed around 1970 and is much better method than the Wurtz reaction in preparing for alkanes containing higher number of the carbon atom than the reactants. Then it consists of reaction between alkyl halide and the lithium dihalide copper. Alkyl halide plus lithium dihalide copper, then it forms the alkanes. R and R may be same or the different. For example, N-butyl bromide plus lithium dimethyl copper, then it forms the N-pentane plus methyl copper. Lithium dialkyl copper required in the reaction, it is usually self-prepared from alkyl halides is stated below. To obtain good yield or alkanes, alkyl halide used generally a primary alkyl halide, while the diethyl group is lithium dialkyl copper may be primary, secondary or tertiary. An important feature of this reaction is that it can be used for preparing all type of alkanes, whether the symmetrical or unsymmetrical, whether state chain or branch chain. Mechanism: it is bringing the alkyl group of alkyl lithium displays halogen from the copper first and the halides to form the alkyl copper. Alkyl copper reacts with the alkyl lithium to form the lithium dialkyl cuprate. Alkyl halides then undergoes nucleophilic attack to the dialkyl cuprate anion to generate an unstable intermediate which decomposes to give the final products. If there is a Kolbe electrolysis reaction, in this reaction concentrated aqueous solution of the sodium or potassium salts of monocarboxylic acid is subjected to hydrolysis to get alkanes. The reaction takes place as follows. In presence of ionizations, the discharge potential of H positive ion is lower than of Na positive. Therefore, H positive ions are discharged as the cathode, liberating H2, while Na ions remains in the solution. Sodium ethanoate or sodium isonate form the CS3CO negative plus Na2 positive. 2CS3CO negative plus minus 2 electrons, then it forms the 2CS3CO is an intermediate, then it forms the ethane plus CO2 gas. 2H positive plus 2 electrons, then it forms the H2S cathode. This is a good method for preparing ethane and higher alkanes having each number of the carbon atoms. Methane cannot be prepared by this method. Sixth is decarboxylation of monocarboxylic acid when the heated when the sodium lime when NaOH plus CO sodium salt of monocarboxylic or fatty acid undergoes decarboxylation to form the alkanes. The reaction involves the elimination of the carbon dioxide from carboxylic group. Active compounds of the sodium lime is the reaction NaOH, but in the employed such as reaction is melt undergo the displacement as well. Sodium salt or fatty acid plus NaOH in presence of CO, then it forms the alkanes. Sodium acetate, then it forms the methane. Oak wood or co-workers 1950 have been shown that the reaction proceeds according to the above equation only in case of sodium acetate. In case of higher members, various side products are also generated. This is in case of sodium propanoate, the reaction gives methane, the hydrogen, and certain saturated hydrocarbons also in addition to the ethane. It may be pointed out the alkanes are also formed during the same other chemical reactions, but the reactions are employed for the actual preparation of the alkanes either groups because of poor yield of the desired products or same carbon products. Preparation of methane. Beside methods numbers 2, 4, 6 discussed above, methane also can be prepared conventionally by dropping water over aluminum carbide. Aluminum carbides then it forms the methane. The gas obtained by this method is generally contaminated by the hydrogen and acetylene. Preparation of the ethane. Although ethane can be prepared by the general method of the preparation, it is generally prepared by the laboratory by the reduction of the ethyl iodide or ethyl bromide with nascent hydrogen reduced by the action of zinc, copper, couple or ethyl alcohols. Ethyl alcohol in presence of CO then from the zinc ethanoid. Ethyl iodide from the CH3 ethane plus HI. Physical property of alkanes. Physical state. The lower member of the alkanes containing up to the 4 carbon atoms are colorless gas. The higher number normal alkanes having 5 to 17 carbon atom or colorless liquid. They are beyond they are colorless solid as room temperature. Then is boiling point. The boiling points of the alkanes increase regularly with the increasing number of the carbon atoms. There is an increase of about 20 to 30 degrees for each carbon atom added to the chain, except in the first few cases where the increase is much more. This can be explained in terms of intermolecular forces of attraction. Alkanes are non-polar compounds having weak van der Waals forces of attraction between their molecules. These forces are set along the surface of the molecule and their magnitude increase with increase in surface area. As the molecular size of alkanes increase, the surface area and strength the van der Waals forces also increase. As a result, the boiling point also increases. Amongst the isomeric alkanes, there are small differences in the boiling point of the various isomers. The branch chain isomers having invariably lesser boiling points, and the normal compounds are the first branching. The lower is the boiling point of the branch isomers. The instance of the boiling point of N-pentane, isopentane, and neopentane are 309, 301, and 285 Kelvin respectively. This is due to the that is branch isomers are more compact. They are lesser surface area, and the normal due to the lesser surface area of the molecules, van der Waals forces of attraction are separating between the atoms are comparatively weaker as lesser energy is needed to overcome the forces boiling point to take place, and therefore boiling points are all lower. Melting point. The melting points of alkanes do not show a very smooth graduation with the increase in molecular size. For instance, let us consider the melting point of N-pentane and N-octane. Let us in some melting point of the hydrocarbons. It may be seen the increase in melting point is much more is moving from the alkanes odd number of carbons atom of the higher alkanes, and the moving from the alkanes having the even number of the carbon atom of the higher alkanes. This is essentially because the intermolecular forces at crystal depends only upon the size of the molecule, but not also upon how well the molecules fit into the crystal. That is, it has been already made clear that the carbon in the alkanes from zigzag type of the chain rather than the straight chains now in containing an even number of the carbon atoms. The terminal methyl groups lie on the opposite side of the zigzag chain. On the other hand, in case of alkanes having odd number of the carbon atoms, the terminal methyl groups lie on the same side of the chain is shown below. in hexane and heptane. It appears that alkanes having an odd number of the carbon atom do not fit so closely together in the crystal structure as the alkanes having an even number of the carbon atom. As a result, the energy required to break the crystal structure and thus melt the alkanes has less cares of alkanes having odd number of the carbon atoms. That is why they are lesser accepted. Melting point has shown only a slight increase in melting point in moving from even number alkanes to the higher number alkanes. Specific gravity. The specific gravity of alkanes also increases with increasing molecular weight, but it becomes constant at about 0.8. This implies that the alkanes are higher than water. Solubility due to the nearly some electronegatives of carbon and hydrogen atom present in them. The symmetrical shape of the molecules alkanes are non-polar in character as they are soluble in water solvents such as water, but dissolve freely in non-polar solvents such as ether. The solubility decreases with the increase in molecular weights. Chemical properties. The molecular structure of the alkanes involves only carbon, carbon and carbon, hydrogen singles bondless. Their sigma bonds are practically non-polar in nature. Alkanes constitute a rather reactive class of compounds. They are quite insert towards the common reagents such as acid, alkalis and oxidizing or reducing agent under ordinary condition. However, under the condition alkanes do not undo under a few reactions mostly involving a substrate. The reactions generally take place by the free radical mechanism. The important reaction of the alkanes are discussed below. First is halogenation. The reaction involves the replacement of the one or more hydrogen atom of the alkanes by the responding number of the atom. Chlorination and bromination are carried out better in the alkanes with the chlorine or bromine in presence of light sunlight or ultraviolet light or the high temperature to 525 to 673 Kelvin. For example, the HNO reacts on methane undergo these conditions and for hydrogen atom the methane are successfully replaced by the chlorine atoms as shown below. Methane in plus Cl2 then from the methyl chloride or CH3Cl then plus Cl2 then form methylene chloride. CH3Cl plus Cl2 then form the CHCl3 chloroform. CHCl3 plus Cl2 then it forms the CCl4 then it is carbon tetrachloride. Bromination through similar of the chlorination take place less readily. Ionization is extremely slow and reversible. CH4 plus I2 then it form equilibrium then it form the methyl iodide plus HI. Therefore, the distinct ionization of the alkanes cannot be brought about. Therefore, the reaction may be carried out by the presence of the oxidizing agents such as iodic acid, nitric acid, and which converts by the hydraulic acid and produces into iodine. 5HI plus HiO3 then from the 3HI2 plus 3H2. Fluorination. The fluorination of the alkanes is not generally carried out it takes place with the repulsive violence. Moreover, the fluorination often involves extensive rupture of the carbon-carbon as well as carbon-hydrogen bonds. The reaction can be made less vigorous or diluting fluorination of the inert gas such as nitrogen or argon. It is obvious, therefore, that is the order of the reactivity of the halogen towards alkane is fluorine, chlorine, then bromine, then iodine. Halogenation of the higher alkanes. Formation of isomeric halogen derivatives. The halogenation of the higher alkanes yield a mixture of all possible isomers halogen derivatives. For example, combination of the propane gives a mixture of 1 chloropropane and 2 chloropropane. Further chlorination gives a mixture of the 4 distribution of the products which are shown below. The mechanism of halogen discussed a little later. Second is nitration. The reaction involves the substitution of a hydrogen atom of alkanes by a nitro group. It is carried out by heating the hydrocarbon in the vapor state with the nitric acid at about 700 Kelvin. Alkanes at 700 Kelvin temperature then from the nitroalkanes. During nitration, rupture of carbon-carbon bonds in the sum of the molecules that take place. As a result, the reaction furnishes a mixture of the different products. For example, the nitration of the propane result in the formation of a mixture of 4 nitro compounds as shown below. It forms 1 nitropropane, 2 nitropropane, nitroethane or nitromethane. Sulfonation is a reaction involving the replacement of hydrogen atom of the alkanes by sulfuric acid group. Only higher alkanes undergo sulfonation by reacting with sulfonic acid. For example, hexane. Then it forms the hexane sulfonic acid. Nitrogen and sulfonation are believed to take place in free radical mechanisms. For this oxidation combination Such as combination when burst in excess of air or oxygen, alkanes undergo complete oxidation by the process of carbon dioxide, water and gas, large quantities of heat. CnH2n plus 2 plus O2 excess NCO2 plus N plus 1 H2O plus heat. In spite of being a highly exothermic reaction, combination requires a high temperature that is flame at start. This is due to the energy of the activation required to initiate the reaction. Due to the large quantities of heat produced during the combustion of alkanes, this reaction has tremendous practical importance. Vast quantities of the hydrocarbons obtained from the petroleum are used as fuel for the production of the heat of power of combustion. The cooking gas commonly known as the LPG liquefied petroleum gas is a mixture of the propane, butane, compresses liquid. Incomplete combustion of the alkanes due to the insufficient supply of the air oxygen result in the formation of the soot or carbon black. This is used in the manufacture of the Indian ink, premister ink as filter ribbons. In this catalytic oxidation, when it is regulated supply of the air oxygen at pressure and the low patience of the suitable metallic catalyst, lower alkanes are oxidized to alcohol and aldehyde, and higher homologs yield long chain fatty acid. For example, when a mixture of the methane, oxygen, and stable properties is compressed at 100 atmosphere and passed through the copper solid at 475 Kelvin, methane is oxidized to methanol. When a mixture of methane and oxygen is passed through the heated malodorine oxide, the methane is oxidized to form formaldehyde. This formation then it forms the CHCHO plus. Normally, alkanes suggest the action of the oxidizing agents such as potassium permanganate, but alkanes containing tertiary halogen atoms can be oxidized to such reagent to corresponding alcohol. For example, isobutane from the dibutyl alcohol. 5 is thermal decomposition or pyrolysis. This process involves the decomposition of higher molecules into a number of simple molecules by the action of heat. When heat is about 575 to Kelvin, higher alkanes undergo processes of yield smaller molecules. For example, propane decomposes follows at about 735 Kelvin. It is apparent that the process involves the decomposition of the carbon as well as carbon-hydrogen bond. The composition of the products depends upon the nature of the starting compounds and the condition of the employees. The process of the thermal decomposition of the alkanes obtained from the petroleum is commonly referred to as the cracking or fragmentation. Cracking is an important process from a commercial point of view and discussed as below detail under petroleum. So is catalyzed for mourning and amortization. This process concerns the conversion of the aliphatic hydrocarbon into the aromatic hydrocarbon. In presence of stable catalytic, the reaction involves the hydrogenation, calcination, and even isomerization. In these cases, it is internally carried out in the high temperature about 720 to 820 Kelvin. High pressure is 10 to 20 atmosphere in presence of the catalyst, which generally contains the chromic oxide spot is aluminium oxide and N-hexane in the hexane and N-heptane in the toluene. N-hexane is converted into benzene and the N-heptane is converted in the toluene. These reactions, the mechanism is generally carried out with the 670 Kelvin presence of platinum as a catalyst. Therefore, the reaction is sometimes termed as plate forming. 7 is isomerization. It is the process of converting one isomer into another. It is found when an alkane are heated in the presence of aluminium chloride and hydrogen chloride, then they are converted into branch chain isomers. For example, an hexane is converted into 2-methylpentane or 3-methylpentane. 7 is mechanism of the halogenation of the alkanes. Mechanism of halogenation. The halogenation of the alkanes is known as the free radical chain reaction. This is because it proceeds through a series of the steps involving free radicals. Each step generating a free radical that brings out the next step till the chain of these steps is finally broken. There are three fundamental stages of the chain reaction, namely the chain initiating step, chain propagating step, chain terminating step. Let us discuss the mechanism of halogenation of the consider the chlorination of the methane. First is chain initiating step. The reaction is initiated by the homolytic cleavage of the chlorine molecule in the two chlorine atoms or free radicals, each carrying an odd or unpaired electrons. The energy required for this is supplied or by heat or light. Cl, then it forms the two Cl free radicals. By first, second is the chain propagating stem. Once the chlorine atom or free radicals are formed, each of them are methane molecules forming hydrochloric acid generating a methyl radicals as shown in step 2. The methyl radical in turn reacts with another chlorine molecule. form methyl chloride and at same time generates another chlorine atoms or free radical as shown in the step. These newly formed chlorine atoms can react with another molecule of methane as shown in the step 2. They produce another molecule of the hydrochloric acid and another methyl free radicals. The methyl free radicals can again repeat the first step 3 and so on. Thus the step 2nd and 3rd are repeated several times. And the chain gets propagated till it is ultimately terminated. Chain propagating step which are repeated several times. The chlorine atoms per step in 3 can also react with the methyl chloride form to yield hydrochloric acid and a new substituted methyl radical as shown in step 4. The substituted methyl radicals react with another molecule of chlorine to form the dihalogenated methane as indicated in step 5. Theoretically, this process may be extended further till as the replaceable hydrogen atom in the methane molecules have been substituted by chlorine. Says chain terminating such chain of the reaction initiated. The probability as outlined above may be determined by the free radicals combined amongst themselves without giving rise to a new radical as shown below. Possible chain terminating steps. The chances of free radicals combining amongst themselves are very slow indeed because of very small relative concentration of the free radicals in the reaction in mixture. Still, such a combination cannot be completely ruled out. As this happens, the chain of the step initiated in the cleavage of the particular chlorine molecule comes to an end, but the other similar chain initiated the cleavage of particular chlorine molecules come to the end, but another chain initiated the other chlorine molecule contains the operate and therefore the overall reaction gives and propagation. Evidence in support of the above mechanism, the free radical mechanism of the halogenation is supported by the following steps. First is the reaction does not take place in the dark of the ordinary temperature but requires energy in the form of heat. 525 to 675 Kelvin or light or initiate the process. This is because the reaction initiating step involves the dissociation of a halogen molecule and a free radical which requires the supply of the energy. Third is high quantum yield. For each photon of the energy absorbed, many thousand molecules of the alkyl halides are formed. This is evidently due to the repeating chain providing step. It has been observed the addition of substances that are source of the free radicals can initiate the reaction in the dark of temperature below 525 Kelvin. For example, the presence of 0.02% of the tetrahalide lead pubic chlorination of the methyl proceed in the dark of at 415 Kelvin. It is also known as the 415 Kelvin tetraethyl lead decomposes to give metallic lead and ethyl free radicals. It appears quite reasonable that the ethyl radical formed in the manners attack chlorine molecule to produce chlorine atom or free radicals. The chlorine atoms thus generated and start the chain providing step and the reaction progresses. Similarly, the reaction proceeds at a low temperature in the presence of benzyl peroxide because it generates the free radicals at lower temperature. Fourth is rule of inhibitors. An inhibitor is a substance that can slow down or although stop a reaction even when present in small quantities. Has been observed that oxygen reacts as an inhibitor in the halogenation of alkanes. It is due to the fact that an oxygen molecule combines rapidly with an alkyl radicals to form the comparatively much less reactive propyl alkyl radicals. As the new radical cannot continue the chain gets terminated. Thus, each carbon oxygen molecule break a chain by the combining with the alkyl radicals and thus stops the formation of the thousands of molecules alkyl head. This naturally slows down the rate of the reaction. Of course, when all the oxygen molecules have been used up, the reaction proceeds normally. Some important aspects of the halogenation of the alkanes. We will now discuss some important interesting aspects of the halogenation of alkanes. Reactivities of halogens in halogenation of alkanes. The order of the reactivity of the halogens in the various halogenation reactions has been found F2, then Cl2, then Br2, then I2. In fact, in case of iodine, the reaction does not seem to be take place at the all. We would try to account for this observed order of the reactivity of considering the energy changes during the chain heating and propagating step in the reaction of the particular reaction. Same methane with different halogens. Since the energy of the activation has not been measured for the various steps of the alkanes, the value of the del H for the different steps derived from the bond dissociation energy would be a lot of help us. The value of del H for each of the three most important steps during halogenation of methane with different halogen are as follows. The first step primarily involves the dissociation of the hydrogen molecule, with therefore del H can be taken as equal to the activation energy of activation. This iodine having the at least activation of energy should dissociate most rapidly, followed by the fluorine, bromine, chlorine in this order. For the order of dissociation goes against the observed of the reactivity of halogen. This means the first step cannot be responsible for the observed order of the reactivity. The third step involving the first reaction of methyl radical with halogen is found to be exothermic in over 4 cases, and the value of the del H is nearly the same for the chlorine, bromine, and iodine. For all these reactions, activation of energy is accepted to be quite small, and actual value of the possible are more than the refraction of the kilojoule in any case. Thus, this step also cannot be explained. The observed activity as appears in this space with equal C's is on all cases. Coming to the second step, which involves the abstraction of the hydrogen of methane by halogen atoms, we observe a wide variation in the various values of del H. The values of activation energy for this step are found to be 70 kJ and 75 kJ respectively for the reaction involving chlorine and bromine atom. In case of the highly exothermic reaction with fluorine atoms, the activation of energy is accepted to be very low, about 1 to 2 kJ, while for the highly isothermic reaction with iodine to atom activation energy must naturally be at least 138 kJ. This implies that the fraction of the effective collision in this step should be in order fluorine, chlorine, then bromine, then iodine. In the reaction of the fraction of the effective collisions, each controls the overall reaction. For instance, so actual reaction of effective collisions between the chlorine atoms and methane is found to be 1 to 48, 548 Kelvin, while in 1 to 10 million in case of bromine atom and methane at the same temperature. Due to the very small fraction and effective collision with methane, it is quite likely to be bromine atoms may happens to collide against another bromine atom as a methyl radical during the search of properly oriented methane molecules and effective collision within it. This means the chain reacting involving a particle bromine with any terminated for long. It is found actual practice that average chain length involving a bromine is less than the 100, while in the case of chlorine it runs into several thousand. It is therefore evident that the rate of chlorination of the methane and the other alkanes should be much faster than the bromination, in spite of where the chlorine molecules dissociate into atoms. First step more slowly than the bromine molecules. In case of fluorination, fluorine atoms are not only formed faster than the chlorine or bromine atoms due to the lower activation energy of first step 1, but also the length of the reaction chain are much longer due to the activation energy of step 2 being only about 1 to 2 kJ. At the same time, the overall formation is highly isothermic, del H being to 427. Especially in case of the overall process of fluorination, chlorination, and bromination, all these factors taken through up justify the implosive nature of the fluorination of alkanes. For in iodation of the carried out activation energy for the second step must be at least 138 kJ. Even this value of the fraction of the effective collision between the methane and iodine atoms works out to be 1 to 10 h to power 10 12 to 4 at 548 Kelvin. Evidently, this is too low a fraction of really allow any reaction propagating chain is functioning. This is why addition takes place only in exhibit rate, although the iodine atoms are found from their molecules completely faster than due to the addition of step 1. It may be noted that the most vital step in halogenation, step 2, involves the formation of the halogen acid. Now, the bond dissociation energy is the order of the reaction. Halogen bond strength may be shown as the same order of the reactivity. Halogen is halogen depth alkanes. This indicates the reactivity of the halogen towards alkanes is linked with the strength of the halogen bond. The more the strength of the halogen, the more the reactivity of the strength of the halogen alkanes. Is the transition state of halogenation, and it has been directly stated that the vital step in the halogenation of alkanes is the energy of the activation of the step which control the overall process is visually equal to the difference in the energy between the reactants and the transition. Let us have a close look at the transition state of the formation of the which is important for the progress of the halogenation. In this transition state, the carbon hydrogen bonds of the alkane is somewhat scheduled that not completely broken. Finally, new new hydrogen halogen bond has been partially formed at the same time. The old electron, which is halogen in case of reactants and alkyl group in case of product, is divided between the two in the transition state. For this repeating such a and dotted line may be used for the indicating partially broken or partially formed bonds, while the symbol a sigma may be employed for the representing each atom's share of the odd electrons, as shown below. Reactant energy from the transition state, energy from the products. The transition state leading to the formation of the particular free radicals has some of the properties of the free radicals. The free radicals and corresponding transition state have the same order of the stability and ease of the formation. Relative reactivities of alkanes in halogenation and relative reactivities of the different classes of hydrogen atoms. It is a mixture of equimolar amount of the two or more alkanes is allowed to react a limited quantity of chlorine or bromine. The product obtained consists of a mixture of different alkyl halides corresponding to the alkanes decks. But the relative quantities of the alkyl halide in the mixture of the two are the same. The means the different alkanes exhibit different degree of the reactivity while reacting the particular halogens. These relative reactivities of alkanes cannot be attributed to the reactivity of the different classes of the hydrogen atom represented in them. It has been found that in perspective of the alkanes in which they are representative of the relative reactivity of the hydrogen follow the order the tertiary, the secondary, the primary, the hydrogens of the methane being lesser reactive than in one primary halogen. To idea of magnitude of the difference in the reactivity of different hydrogen atom, let us consider the reaction between a mixture of equimolar amount of ethane and methane or small quantity of fluorine at 298 Kelvin. In the presence of light is found to amount of ethyl chloride from about 400 times as much as the methyl chloride. This means the ethane is 400 times as reactive as methane, allowing that the ethane of the 6 hydrogen atoms, while methane has only 4. The primary halogen is still about 267 times as reactive as hydrogen as methane. The reactivity of the different classes of the hydrogen atom may be explained by the considering the reactive stabilities of the alkyl radicals formed in the step which control the overall process of the halogenation. For instance, case of chlorination of methane and ethane are respective rate controlling step may be written as relative to the respective parent alkynes. Ethyl radical, a primary radical is stable than the methyl radical as such, and the transition state leading to the formation of the radicals must be more stable than the transition state generating ethyl radicals. Consequently, the transition state of the ethyl radical must have less reactivation energy than the transition state of the methyl radical. Therefore, the transition state is the former case lesser reactivation energy. The transition state of methyl radical, therefore, the transition state former case must be obtained readily than the latter. In other words, the carbon hydrogen bond in the ethane gas, the stretch and ultimately breaks more is rarely than the carbon hydrogen bond in methane. That is why the primary hydrogen atom in the ethane are said to be more reactive than the even hydrogen atom in the methane. Similarly, the still greater reactivities of the secondary and tertiary hydrogen atoms can be explained in terms of greater stability of secondary and tertiary alkyl radicals. Thus, it may be concluded that the reactivity of the different classes of hydrogen atom, which determine the reactive rate of the halogenation of different alkanes, follow the same order as that the reactive rate stability corresponding of alkyl radicals, that is tertiary, then secondary, then primary, then the methane. Orientation of the halogenation, it has been observed that sometimes a compound can form different products and reaction while the same reaction. This means that the compound has made the once reactive site where the attack to the given reagent can take place. The process determines the particular state site in where the reaction is most likely to occur is also as orientation. It involves the examination factors which can influence the relative rate of the competing reaction. For the present, let us consider the orientation variation of alkanes. It has been pointed out earlier that the halogen of higher alkane can lead to the formation of the two or more isomeric products. For instance, the chlorination of the propane at room temperature products a mixture and propyl chloride and isopropyl chloride are in ratio 45 to ratio to 55. The rate controlling step in the two competing reactions involves the formation of N-propyl and isopropyl radicals by the aberration abstraction of the primary or a secondary hydrogen or propane is shown below. Normally, the relative quantities of the two halide products would depend upon the relative rates at which n propyl and isopropylitic are formed. Let us consider the various factors. Collision properties factors are and energy factors which can influence the rate of the formation of these radicals. First is collision friction. As therefore collision friction is the side is must be same for the two reactions since they are same particles. And next topic is cycloalkanes in the unit of alkanes. Introduction. Cyclic aliphatic hydrocarbons or alicyclic hydrocarbons are hydrocarbons which contain closed chain or ring of carbon atom and resemble open chain or aliphatic hydrocarbons in many aspects like aliphatic hydrocarbons. Alicyclic hydrocarbons may be saturated or unsaturated in nature. Saturated cyclic hydrocarbons are generally known as cycloalkanes. They have the general formula CN2H2N and isomers with alkanes. In this chapter we shall discuss the chemistry of cycloalkanes, nomenclature of cycloalkanes. Common name. Saturated alicyclic hydrocarbons contain a number of methylene groups joined together to form a ring. Therefore, they are known as polymethylenes in the common system. Accordingly, the individual members are named by the prefixing the number of carbon atom in the ring before the word methylene. For example, trimethyl, tetramethylene, hexamethylene. IPC system. In the IPC system, saturated alicyclic hydrocarbons are termed cycloalkanes. The individual members are named by the adding the prefix cyclo to the name to the corresponding state chain. Hydrocarbons having the same number of carbon atom as the ring. For instance, cyclopropane, cyclobutane, and cyclohexane. Quite often, alicyclic hydrocarbons are also represented by drawing simple geometric figures such as triangle of cyclopropane, a square for cyclobutane, a pentagon for cyclopentane, and so on. In the presence of a carbon atom at each of the corners and hydrogen atom attached to the carbon is taken for granted. For example, cyclopropane, cyclobutane, cyclopentane, and cyclohexane. Nomenclature of such substituted cycloalkanes. IPC name. The substituted cycloalkanes are assigned by the following. The IPC rules with the students are already studied. However, some important points are given below. For monosubstituted cycloalkanes, there is no need of numbering to indicate the position of the group. For example, methyl cyclohexane. Second is for cycloalkanes containing more than one substituent. The members of the carbon atom of the ring is done in such a way that the substituent get the lowest possible number. Their number are prefixed in alphabetical order although with their positions. Position moreover, the substituent which comes first in alphabetical order gives the lowest possible number provided it does not violate the whole lowest set of locant rule. For example, 1,3-dimethyl cyclopentane, 4-ethyl 1,2-dimethyl cyclohexane, and 1-ethyl 2-methyl cyclopentane. Third one is if the ring contains equal or more number of carbon atoms and the alkyl group attached to it, the compound is named as the derivative of cycloalkanes and the alkyl group is taken as a substituent as already shown above. If the ring contains lesser number of carbon atom and the alkyl group attached to it, and if more than one ring is attached to a single chain or compound named as the derivative of alkane, and the alicyclic ring is treated as a substituent. For example, 2-methyl 1-cyclopropylbutane and 1,3-dicyclohexyl propane. In addition to the above rules of cycloalkanes, more important for naming cyclocompounds containing multiple bonds and the functional group are given below. First one, if the carbon chain attached to the alicyclic ring contain a multiple bond or a functional group, the carbon chain is taken as the parent and the ring is treated as a substituent irrespective of the size of the ring. First is the 3-methyl 1-cyclobutane 1-ene. Second is 1-cyclohexyl butane 2-one. Second is one is if a compound contains alicyclic ring directly attached to a benzene ring, it is named as the derivative of benzene. For example, the cyclohexyl benzene in 1,3-methyl cyclohexyl 4-nitrobenzene. Third one is if the ring contains a multiple bond and the side chain contains a functional group, the ring is treated as strain and the compound is termed as a derivative of the chain containing the functional group. For example, the 4-cyclohex 2-enyl but 1 in the fourth point is if a functional group containing carbon is directly attached to the acyclic ring and the carbon atom of this group is substitutively included in the suffix for the used group. For example, CH group is represented by the suffix carbaldehyde or the carboxylic acid and the carbonitrile. Synthesis of cycloalkanes and their derivatives only method 357 included in the table. The important method of synthesis of cycloalkanes and the derivative discussed where most of this method it may be noted involve the conversion of some open chain compounds into a cyclic compound through the process is cyclization or ring closure. The cyclic compound thus obtained by a cycloalkane and its derivative it required the cycloalkane derivative is further subjected to a substitutable reaction to change into it desired cycloalkanes itself. First, in addition to the carbenes to alkanes, this method involves the addition of carbenes to alkene to form the cyclopropane derivative. This reaction is also referred to as cycloaddition. Since free carbenes are too reactive to isolate, the reaction is actually carried out by using a carbene precursor that generates the carbene under suitable experimental conditions. For example, when treated with diazomethane CH2N2 or ketene CH2 double bond C double bond O in the presence of light, alkanes add to a carbene to form the cyclopropane derivatives. Alkanes plus diazomethane and in the presence of sunlight then form the substituted cyclopropane. Second is Siemens-Siemens reaction. In this method, addition to the carbenes is carried out by treating the alkanes with methylene iodide CH2I2 and the zinc copper couple to get cyclopropane derivative. For example, Zn-Cu couple required for the reaction is usually obtained by the heating Zn dust with CuCl in the ether with the presence of nitrogen. It is believed that the methylene iodide and zinc react to form the carbenes like a species called the carbenoid. CH2I2 plus zinc copper, then it forms the ICH2Zn iodomethyl zinc iodide which is carbenoid. The carbenoid being about the specific addition to the CH2 group directly to the alkene. Siemens-Siemens reaction gives better yield of cycloalkanes than in the obtained by the addition of the free carbenes to alkenes. Third one is photochemical 2+2 cycloaddition reaction. The term cycloaddition denotes an addition reaction between the two unsaturated molecules to form the cyclic product. During these reactions, assigned bonds are formed in the cost of pi bonds. The reacting molecules in these reactions are designed by the writing the number of pi electrons of each reactant in a square bracket. For example, a reaction between two alkanes molecules to form a cyclobutane by using 2 pi electrons of each molecule is referred to as 2+2 cycloaddition. 2+2 cycloaddition reactions can be carried out easily in the presence of light but not under thermal conditions. Such reactions are termed as photochemical 2+2 cycloaddition reactions. They take place by a concentrated mechanism involving cyclic transition state. The formation of substituted cyclobutane by photochemical 2+2 addition of the two alkanes molecule can be represented as the formula alkanes 2 molecules in presence of sunlight and form the cyclic transition state, and after that it forms saturated cyclobutane. Fourth one is 4+2 cycloaddition dies alter reaction. 4+2 cycloaddition reaction involves the addition of the alkanes 2 pi electrons referred to as dinephylene and a concentrated dienes 4 electrons to form 6-membered system. In contrast to 2+2 cycloaddition, these reactions take place rarely under thermal condition. For example, 1,3-butadiene diene plus ethane diphenyl, then it forms the cyclohexane. The diphenyl's electron containing group the reaction takes place extremely easily, sometimes even at the room temperature. For example, 1,3-butadiene, then it forms the 1,2,3,6 tetrahydryl benzylaldehyde. It is interesting to note that 2 plus 2 cyclic addition reaction take place readily photochemical but not thermally. On the other hand, 4 plus 2 cyclic addition reaction occur readily thermally but not photochemically. Fifth oxidation is dihalogenation of suitable dihalogenate derivative of alkanes. Front method on this treatment of suitable alpha dihalogen derivative of alkanes. Dihalogen derivative having the halogen atom attached to thermal carbon atom with sodium or zinc, they get halogenated to form cycloalkanes. For example, 1,3-bromo dibromopropane, then it forms plus zinc, then it forms cyclopropane. 1,4-dibromobutane plus zinc, then it forms the cyclobutane. This method may be regarded as the internal Wurtz reaction. However, this method gives good yield only in preparation of cyclopropane. If the alpha or gamma dihalide contains more than 6 carbon atoms, intermolecular Wurtz reaction takes place, giving rise to the open chain alkanes. Sixth one is dicarbon cyclization. When ester contains dicarboxylic acid with a diaphilic acid and phenolic acid and treated with sodium or sodium ethanoate, undergoes intermolecular collision condensation to yield cyclic beta ketoester. The beta ketoester on hydrolysis and heating at the dicarboxylated to form the cyclic ketones. The ketones are in turn subjected to the Clemenson reduction to get the cyclic alkanes. Dicarbon method is most suited to the preparation of 5 or 6 member rings. Second is pyrolysis of calcium or barium salt of carboxylic acid method. When the calcium or barium salt of certain dicarboxylic acid are heated strongly, they yield a cyclic ketone. The ketone thus formed and converted into cycloalkanes through Clemenson reduction as stated below. Calcium modified in presence of then it formed the cyclic pentanone, then it formed the cyclopentane. In given the Planck's rule given below, the method is used for the preparation of 5-6 membered ketones. Planck rule. This rule was formulated for the Planck on the basis of experimental observation of the ease of formation of cycloanhydride and ketones by distillation of the dicarboxylic acid according to the relative position of 2 carboxylic group. According to this rule, distillation of 1,4,1,5 dicarboxylic acid give rise to the cyclic anhydride, while 1,6 and 1,7 dicarboxylic acid yield ketones. 1,8 higher dicarboxylic acid remains unaffected. Planck's rule can be used for determining the size of the ring as well as chain length of the dicarboxylic acid. For this purpose, a double bond is introduced by stable method in the given compound whose ring size is determined. The unsaturated carbons compound thus obtained in subject oxidated cleavage with cheminophore to get the dicarboxylic acid. This acid is treated with acetic anhydride and distillated. If a cyclic anhydride is obtained as a product, the acid is ether 1,4,1,5 in nature. If a cyclic ketone is formed, the acid is 1,6 and 1,7. There is no change acid in 1,8 higher. The structure of acid is reverse the size of the ring. It is Thopper-Ziegler reaction on the heating of presence of lithium dimethyl and dinitrile in the nitrile group attached to the terminal carbon atom undergo intermolecular condensation to form the cyclic amino nitrile. This is changed into cycloalkanes as stated below. The first step in the reaction involving the cyclization takes place only at the very high dilation. It is referred to as the Ziegler high dilation technique. Thopper-Ziegler reaction is particularly stable for the preparation of higher ring compounds. Ninth is Desmond rearrangement. This reaction provides a method of expanding and contrasting alicyclic ring system through the formation of the carbocations. The carbocations themselves are obtained by the diminution of alicyclic amine by treating with nitrous acid. One form the carbocation undergoes characteristic reaction, that is addition of nucleophile. Second is elimination of a proton. Third one is rearrangement of a more stable carbocation. As a result, different products are formed, including ring expansion or ring contraction products as illustrated below. Ring expansion when cyclobutyl methylamine. One is treated with the nitrous acid to get four products: cyclobutyl carbonyl third and the methyl cyclobutane second, and formed without involving the ring expansion. At the same time, cyclopentane fourth or cyclopentane 5 are formed by the ring expansion. Ring protection: when the cyclobutylamine 6 is treated with the nitrous acid, cyclobutyl 8 is formed without any ring protection. At the same time, the cyclopropyl carbonyl 8 is formed by the ring protection. It may be noted that when the carbocation initially formed carried the position change, xylocyclic carbon is lead to the ring contraction. On the other hand, when the initially formed carbocation carries the positive charge on the carbon, A is to the cyclic ring and expansion take place. Then is the hydrogenation of aromatic compounds cyclohexane, and the derivative can be also prepared by the hydrogenation of benzene and its derivative. For example, benzene plus 3H2 in presence of nickel at a temperature of 423 to 473 Kelvin, that it forms the cyclohexane. 11th is condensation of stable dihalide with malonic ester or acetoacetic ester followed by the hydrolysis and dicarboxylation. In the presence of sodium ethanoate ether, active methylene compound such as malonic ester and acetic acid condense the suitable halides to form the cyclic diester. These are the hydrolysis and decarboxylation yield cycloaklanes. For instantaneous, the methylene dibromide malonic ester then from the cyclopropane dioxide ester. Cyclopropane monocarboxylic acid is then converted into cyclopropane through a sequence of reaction. It is noted that the acid cannot be directly dissociated by the heating. It leads to the cleavage of the ring. Acetoacetic acid may be also is used in the presence of malonic acid in the reaction. The ketone obtained is suitably treated to get the corresponding hydrocarbons. Second is the physical property. In the physical property, cycloalkanes resemble the corresponding open chain compounds, although they are somewhat higher boiling point and densities. For instance, the first two members of cycloalkanes, cyclopropane and cyclobutane, are gases, while higher members are liquids. Second is they are non-polar in nature and such as insoluble in water but soluble in organic solvents. Some of them are cyclohexane are good solvent themselves. Chemical properties. The general chemical behavior of cycloalkanes is similar to that of corresponding open chain hydrocarbons like alkanes. Cycloalkanes also contain only carbon-carbon and carbon hydrogen sigma bonds, and they are therefore quite inert towards the chemical reagent and undergo only a few substituent reactions. It must be emphasized, however, the cyclopropane and cyclobutane differed considerably from their higher homologues. This is because the cyclopropane and cyclobutane are not very stable and they have a tendency to open up and form additional products. As such, the resemble alkanes is undergoing some addition reactions, but they are so unreactive than corresponding alkanes. A few reactions of cycloalkanes are discussed below. First is reaction with halogens. Generally speaking, cycloalkanes undergo free radical substitution with a halogen at a high temperature on the basis of light. For example, cyclohexane plus Br2 in presence of sun, and then form the bromocyclohexane, and the cyclopropane in presence of plus Cl2 in presence of sunlight, then form the chlorocyclopropane. In case of cyclopropane, however, the bromine and chlorine break down the ring system in the presence of FeBr3 or FeCl3 and the high temperature and yield open chain addition products. For example, the cyclopropane plus Br2 in presence of FeBr3, then it forms the 1,3-dibromopropane. Second reaction is a reaction with halogen acid. In presence of cycloalkanes do not react with the halogen acid. However, the cyclopropane acids adds on halogen acid to form the open chain alkyl halides, that is cyclopropane plus H, then it forms the N-propyl iodide, and cyclopropane plus HBr, then it forms the N-propyl bromide, or the cyclohexane plus H, then is no reaction. Third is addition of water when heated with a concentrated H2SO for cyclopropane, but not other cycloalkanes adds on the water to form the alcohols. Cyclopropane plus H2O in presence of H2SO, then it forms the N-propyl alcohol. Fourth one is reaction with hydrogen. When treated with hydrogen in presence of nickel, cyclopropane and the cyclobutane form open chain addition products, while higher cycloalkanes do not react. Reaction of cyclobutane takes place at a much higher temperature than required in case of cyclopropane. Cyclopropane plus H2 in presence of nickel, then it forms the N-propane. Cyclobutane plus H2 at a high temperature, then it forms the butane. Cyclohexane plus H2, then there is no reaction. It may be noted that the cycloalkanes cyclopropane is most active it undergo many addition reactions composed by the ring cleavage. Next come cyclobutane, which undergo addition of hydrogen, while the rest of cycloalkanes do not form addition products. Relative stabilities of cycloalkanes bear strain theory. During the earliest stage of this study, cycloalkanes containing up to only 6 carbon atoms rings could be prepared in the laboratory, and the ring contains 7 or more carbon atoms where the unknown it is. It was also observed quite early that ring open chain alkanes, cyclopentane and the cyclohexanes are quite stable and do not undergo addition reaction. On the other hand, the cyclopropane and the cyclobutane were found to be relatively much less stable and capable of undergoing even addition reaction through ring cleavage. This difference is relative stabilities of the different cycloalkanes with initially explained in terms of base strain theory as discussed below. Base strain theory, according to the tetrahedral concept of a carbon atom bonded to form other atoms lies on the center of the tetrahedron. Angle between the two angle is 109 degree to 28 minutes. Alford von Beers 1885 argued that their departure from the position leads to a strain in the molecule, as a result of which stability of the molecule decreases. On the basis of Beer proposed a theory known as the base strain theory. The important points of theories are: first, in the carbon atom containing the ring lie in the same triangle straightly, the bond angles between the adjacent carbon atom of the ring are no longer remains 109 degree to 28 minutes, which is normal bond angle of a tetrahedral carbon. On the other hand, the different rings have different values of this angle. For instance, the cyclopropane ring is that triangle having a carbon angle of only 60 degree. Second, in any deviation, position or negative from the normal tetrahedral, bond angle is 109 degree to 28 minutes. During the formation of ring products, an internal strain in the resultant molecules, which makes the molecule unstable. Position derivative means that the angle is compressed, while negative deviation means the angle gets expanded. Third one is, the greater the deviation from the normal angle, the greater is the strain through the lesser is the stability is noted. However, the sign of deviation makes no difference. Fourth one is, the more stability the ring system, the more is the easily it is formed. Beer calculated the deviation from the normal angle, but they can be called angle strain involved in the formation of cycloalkanes of the various ring sizes. For example, carbon angle of the cyclopropane ring is 60 degree. Each carbon atom occupies a corner of the equatorial angle. This means the angle strain in cyclopropane would be 1 by 2, 109 degree to 28 minutes minus 60 degree or 24 degree 44 minutes. Similarly, the carbon angle in cyclobutane is 90 degree and the angle momentum is situated at the corner of the square. As such, the angle strain in cyclobutane is 1 by 2 into 109 degree 28 minutes minus 90 degree or 9 degree 24 minutes. The angle strain of cycloalkanes of the various signs are summed in table 4.1. Evidence in favor of Bayes' theory. It is obvious from the bond angle the magnitude of the strain goes on the decreasing as we proceed from the cyclopropane and the cyclobutane. Hence, the formation and stability should show a corresponding increase in the actual found to be shown. The ease of formation and stability of the cyclohexane can be justified in view of the small angle strain in this case. The fact the cycloalkanes having 7 or more carbon atoms are known as to exist at the time of Bayer was attributed the increasingly large strain in the formation of higher rings. Second, the Bayes strain theory could also account for the great reactivity of the ethyl bond. The double bond as treated as a two-membered ring in the presence of angle strain is 1 by 2, 109 9 degree 28 minutes minus 0 degree plus 44 degree 44 minutes. This large strain seems to be resembled to the reactivity of the double bond. Limitation of base strain theory. Base strain theory failed to explain the following. First is the formation of a ethylenic bond. The ethylenic bond can be formed readily in spite of the having a large angle strain. Second is stability of the cycloaklanes at higher cycloalkanes. Heat of the combustion of cycloalkanes. Base strain theory failed to explain the stability of the cycloalkanes and higher cycloalkanes as discussed below. Cyclohexane and higher cycloalkanes may be which have prepared after the base strain theory has been proposed are found to be nearly as stable and cyclopentane are shown by the heats of combustion. The heat of combustion as methylene group CS2 of the various cycloalkanes are given in 4.2 table. Heat of combustion per CS2 group of open chain alkanes is 658.5 kJ per mole. The heat of combustion per CS2 group gives a fair idea of the relative stability of cycloalkanes. Since each CS2 group yield only carbon dioxide and water or combustion, if the heat is combustion is large, a compound containing more energy and is therefore less stable and vice versa. It is immediately apparent from table 4.2 that is compared on the open chain alkanes. Cyclopropane and cyclobutane only give nearly 38 to 28 kJ more energy per CS2 group. This means that they have relatively less stable effect. That is our arrangement with base strain theory. However, the heats of combustion per CS2 group of cyclopentane, cycloalkanes, and cycloalkanes differ only in the very slightly from that of open chain alkanes. This implies the cyclopentane and the higher chain alkanes are nearly as stable as open chain alkanes. This obviously goes against base strain theory, according to which cycloalkanes having more than 5 at carbon atom ring should be increasingly less stable due to the increasing deviation from the normal tetrahedral angles. And it says more theory of the stainless theory. To explain how cycloalkanes having a ring of 6 or more carbon atom are almost as stable as cyclopentane says. In 1890, such put forth a theory of stainless ring of higher member compounds. According to him, carbon atom constituting the rings lie in the same plane only up to 5 membered rings, while the carbon atom in 6 membered higher rings do not lie in the same plane. Since the carbon atom in 6 membered and higher member lie in the different planes and the normal tetrahedral angle remains unaltered, as such there is no angle strain in bigger rings, and that is why they are stable. For instance, says propose the existence of two types of multiplanar and puckered stainless rings known as the chair or boat forms of cyclohexanes. Both these forms are free from angle strain and can be interconverted just by rotation around the single bonds. Thus, they merely represent the two conformations of cyclohexanes and cannot be isolated separately. Figure 4.5, the stainless ring of cyclohexanes. You have to say chain form and the boat form. Similarly, 7-membered and higher membered rings are stainless in nature. Says more theory of stainless rings are further supported and elaborated by Moore 1918 over the compound containing two more fused together. Difficulty encountered in the synthesis of the large membered rings. It may be interesting to know that why bigger rings are rather difficult to synthesize, even though there is no angle strain in them. This is primarily due to the fact that two ends of the chain of atoms must come closer together to take place through induction between the groups present at the two ends. If a chain undergoing ring closer very long, there is relative lesser chances of the two ends come close enough to ring to the form. On the other hand, there is what happens is that the end of the chain Y may interact with the end of the different chain, leading to the formation of the entirely different products. This difficulty is now being overcome by the carrying out ring closure reaction in highly dilute solutions. Under these conditions, the collision between the different chains are minimized when the chain ring closure take place at the main reaction, although a very slow rate. But once the rings are formed, they are quite stable. Band or banana bonds in cyclopropane orbital picture of the angle strain. According to the orbital concept of covalency, a covalent bond can be formed between the two atoms only in two atoms are oriented in such a way that their orbitals can overlap each other. It may be recalled that greater the overlapping of atom orbital is stronger the bond formed. Now the carbon atom of the cycloalkanes and stable of sp3 hybridization and the formation of the covalent bond between the two atom involves the overlap of an sp3 orbital of a carbon atom with similar orbitals of the other. The maximum overlap or bonding should take place in such a way that the bonding orbitals point directly towards each other. Consequently, when carbon atom is bonded to the other carbon atoms, the bonds angle between the be 109 degree to 28 minutes, which is cyclopropane. The bond is only the 60 degrees. This means the cyclopropane is the bonding orbital and the pointing directly towards each other along a straight chain. This is a result overlap. These orbitals take place at a smaller extent, and the bond formed are described as band bonds. These bonds are much weaker than the normal carbon-carbon bonds. Consequently, the cyclopropane molecule is quite unstable, unstrained, and reactive in nature. You have to see in 4 points figure 6. First is maximum overlap of sp3 orbital of carbon is open chain or large chain compounds. B is part is poor overlap of sp3 orbital of carbon is cyclopropane ring. Only orbital concerned in the bond formation zone. In cyclopropane, carbon or angle is 90 degree and the overlap is relatively more effective than in the cyclopropane, as cyclopropane is relatively more stable.